We now discuss the solution of a problem from the section Real Analysis, and the problem is on the concept of limit superior and limit inferior of real sequences. And this question has appeared in CSIR National Eligibility Test held on 26th November 2020, and it is from the section B and it carries 3 marks. The problem is, let f be a function n to n be a bounded function. Which of the following statements is not true? Option 1. Limit superior of fn belongs to the set of natural numbers. Option 2. Limit inferior of f of n belongs to the set of natural numbers. Option 3. Limit inferior of f of n plus n belongs to the set of natural numbers. And option 4. The limit superior of f of n plus n does not belong to the set of natural numbers. Now, we talk about the limit inferior and limit superior of a sequence of real numbers. The limit inferior and limit superior of a sequence xn, n is equal to 1 to infinity, of real numbers is defined by limit inferior of xn is equal to limit n tends to infinity of t suffix n, where tn is the infimum of the set of all xk, k greater than or equal to n. Limit superior of xn is equal to limit n tends to infinity of Sn, where Sn is the supremum of the set of all xk, k greater than or equal to n. And it is known for any sequence of real numbers, limit inferior and limit superior always exist. It is irrespective of limit of the sequence exists or not. And they exist as the real numbers together with plus infinity, minus infinity. Note 1. If the sequence xn is not bounded above, then limit n tends to infinity for Sn is infinity, because the sequence Sn is unbounded and it will be infinity, and so limit superior of xn, n tends to infinity, is infinity. If the sequence xn is not bounded below, then the sequence tn, as n tends to infinity, will be minus infinity, and so limit inferior of xn as n tends to infinity is minus infinity. And limit inferior of xn is always less than or equal to limit superior of xn. Let xn, n is equal to 1 to infinity, be a sequence that is converging to L, then limit n tends to infinity of xn is equal to L if and only if limit superior is equal to limit inferior of xn is equal to L. When the limit exists, limit superior and limit inferior, they are equal and equal to L. Now let us get into the example. We are given f, a function from the set of natural numbers to set of natural numbers, and it is given as a bounded function. That is, the set of all fn, n belongs to n, is a bounded sequence of natural numbers. Now, every sequence of real numbers, its limit superior and limit inferior exists, so also limit superior and limit inferior exists for this sequence of natural numbers. And because it is a bounded sequence of natural numbers, they are positive, that is limit superior and limit inferior are positive and finite because it is bounded. We will now prove that they are natural numbers. That is, the limit superior and limit inferior of this sequence are natural numbers. Let Tn is equal to the infimum of f of k, k greater than or equal to n, and Sn is equal to supremum of f of k, k greater than or equal to n. Clearly, Tn belongs to n, Sn belongs to n because it is a sequence of natural numbers, and Tn less than or equal to Sn. Further, limit inferior of f of n is limit n tends to infinity of t of n. We know this exists. And limit superior of f of n is equal to limit n tends to infinity of Sn exists. And they are positive and finite. Now we claim limit n tends to infinity of t of n is a natural number. Assume it is not. Assume that the limit n tends to infinity of Tn is L, where L is not a natural number. That is, L is a real number but not a natural number. We are assuming this. And we recall the definition of the limit n tends to infinity of Tn is equal to L. This implies for each epsilon greater than 0, there exists a natural number m such that modulus of Tn minus L is less than epsilon for all n greater than or equal to m. This implies Tn belongs to the neighborhood with center L and radius epsilon, which is the open interval L minus epsilon to L plus epsilon for all n greater than or equal to m. Thus, Tn belongs to the neighborhood with center L and radius epsilon, which is equal to the open interval L minus epsilon to L plus epsilon for all n greater than or equal to m. Now let's look at this is the real numbered line, and this is your real number L, and we take the ceiling of L. The ceiling of L. What is the ceiling of L? It is the least integer greater than or equal to L. And note that no natural number lies between L, the real number, and the ceiling L, because it is the least integer greater than or equal to L. And consider the floor L. The floor L is the greatest integer less than or equal to L. So between this floor L and L, there is no natural number, and there are no integers, and thereby there are no natural numbers in our situation. So between floor L and ceiling L, there are no natural numbers. So now we take an epsilon will be as 1 by 2 minimum of L minus floor L, comma, ceiling L minus L. So this distance and this distance, out of this you take the minimum, then make half of it, and consider the neighborhood with center L and radius epsilon. This is the neighborhood, and this does not contain any natural number. So this is a contradiction. So the neighborhood with the center L and radius epsilon does not contain any natural number. And this is a contradiction to Tn belongs to the neighborhood with center L and radius epsilon for all n greater than or equal to m. This contradicts because this neighborhood does not contain any natural number at all. So this contradiction tells you that your L is not a natural number is false. Therefore, your L is a natural number. Therefore, limit n tends to infinity Fn, Tn belongs to n. This implies limit inferior of Fn and n tends to infinity will be equal to limit of Tn that belongs to n. In a similar fashion, limit superior of Fn is equal to limit n tends to infinity of Sn is also a natural number. And let's look at the options, and which of the following statements is not true. So both of them are true, they are natural numbers. So the options 1 and 2 are true. Now let us take a note, and this is a very simple exercise. This result is needed for us. Limit superior of n is equal to limit inferior of n is equal to infinity. So you consider a sequence x and n is equal to 1 to infinity, where xn is equal to n. So xn is equal to n for all n belongs to n. Note down the limit of this is not a convergent sequence, therefore the limit does not exist. Note that limit does not exist. And note that this sequence is not bounded above but bounded below. So it's bounded below but not bounded above. And since it is not bounded above, limit superior of xn will be infinity. And let's now see what the limit inferior for this. Let Tn is equal to the infimum of xk, k greater than or equal to n. That is the infimum of xn, xn plus 1, xn plus 2, etc. And xn is n, xn plus 1 is n plus 1, xn plus 2 is n plus 2, infimum of all those things. The infimum of n plus 1, n plus 2 is n, and for all n belongs to n, and limit n tends to infinity of Tn will be infinity, therefore limit inferior of xn is infinity. So in this example, limit superior is equal to limit inferior of n is infinity, and this result is needed for the next discussion. Let's get into. We have seen limit superior of Fn and limit inferior of Fn. They are all, both are finite natural numbers in our case. Let L is equal to limit inferior of f of n. Now, for any two sequences, an and bn, limit inferior of an plus bn is always greater than or equal to limit inferior of an plus limit inferior of bn. This is a result. So we apply this for f of n plus n. So we talk about limit inferior of f of n plus n. So f of n is one sequence, n is the other sequence. So that will be greater than or equal to limit inferior of the first plus limit inferior of the second, that is limit inferior of n. Limit inferior of Fn is L, limit inferior of n, which we have seen in the last slide, that is infinity, and that the overall it will be infinity. So this implies limit inferior of f of n plus n does not belong to the set of natural numbers. Let's look at our option. And which of the following statement is not true? So here it is given in the option 3, limit inferior of f of n plus n belongs to n, but we got it does not belong to n. Therefore, the option 3 is not true. Now, limit superior of n tends to infinity of f of n plus n is always greater than or equal to limit inferior of n tends to infinity of f of n plus n. And limit superior is always greater than or equal to limit inferior. That is what we have seen in the first slide itself. And limit superior of f of n plus n is greater than or equal to limit inferior of f of n plus n, which we have seen limit inferior of f of n plus n is as infinity as above. Therefore, limit superior of f of n plus n does not belong to natural numbers, and your option 4 says it does not belong to n, so therefore it is true. So therefore the option 4 is true. So in all, we have to find out that statement which is not true. Out of these 4 options, 1, 2 we have already seen they are true, and 4 is also true, and 3 is the only statement which is not true. Therefore, the final answer is the option 3 is not true. So that is the discussion of the solution of the problem from the section real analysis, and in this problem there is a discussion on limit superior and limit inferior of the sequence of natural numbers and the results what we have seen in the example. And I hope that you have understood the solution of this problem, and I wish you all the best. Thank you.